So I'm going to be discussing density functional theory, making connection to what Simo was presenting, and then I will show how we can do high throughput screening with that. And probably there's going to be a part that's going to be in the afternoon for introducing. Okay, so first, the problem that we have to solve, as you all know, is the system of n electron and a number of nuclei that are interacting. And so if we manage to get the wave function of the whole system, so the wave function depending on the position of the electrons and of the nuclei, then we have solved everything. Of course, that's too difficult to handle, and so we make a number of approximations. And the first one is that we separate the movement of the electrons from the one of the nuclei, which are way heavier, and as a result, they are slower, and we can kind of consider that the nuclei are fixed when we deal with the electrons. And formally, the way you do that is that you can separate the variables in the wave functions between those that are purely electronic and those that are related to the nuclei. So once this is done, we're still left with a difficult problem. Once we assume that the positions of nuclei are fixed and we deal with the electron, it's still complicated. And the system that we are interested in is a system of n electrons that are interacting in an external potential Vx, such as the one that is generated by the nuclei. Okay? And so here, what we want to find is the many-body wave functions of the electrons. And so we have to solve the Schrödinger equation that you have there, where we have a sum over all the electrons, and then we have the kinetic energy, the external potential that I was discussing before, and then the Coulomb interaction between the electrons. So if we manage to get the wave function, then we know everything about that system. Okay? So this is the kinetic energy, and this is the Coulomb interaction. Now, one way to solve that, analytically, it's of course not possible, but numerically we can do it. And one way to do that is to take advantage of the variational principle that basically says that if you have the ground state energy of the system, so here I'm taking the bracket for the Hamiltonian divided by the bracket of the wave function, so to normalize it, sorry. If I get that energy, and then I do the same with some kind of arbitrary function that can be called a trial wave function, this energy of this E phi here is going to be bigger than this one because of the variational principle. Okay? And so what we can try to do is to minimize this function of phi here with respect to phi, and we should reach a minimum when phi is equal to psi. So we can exploit that to try to get an energy as close as possible to the minimum. And to do that, we need to have some trial wave function. And so, for instance, if we have a trial wave function that depends on one parameter A, what happens is that we need to evaluate, of course, this energy here, which we can do, for instance, with Monte Carlo techniques. But if we can do that, then we have something that depends on one parameter, and we just need to minimize by using the derivative of this energy as a function of the parameter A. Okay. Of course, this all depends on the quality of the phi that you have found and how accurate it is, the closer you're going to get to the actual minimum of the energy. Okay. Still, this is very complicated because this n electron wave function is a very complicated object. Okay. Let's say that I want to sample a space that I'm dealing with by a 10 by 10 by 10 grid, which is not a lot, okay? My wave function depends on the position of in this case, I'm taking 8 electrons, okay? So in the case of 8 electrons on this 10 by 10 by 10 grid, I need 10 to the power of 24 real number to describe this wave function. So it's a huge amount of information, okay? So if you compare that to classical mechanics, if I had 8 electrons with classical positions at classical velocities, that would be just 8 times 6 numbers, so 48 numbers to describe the position and the velocities of my electrons. And here we need 10 to the power 34. So we're quickly very limited by what we can actually do with this approach, okay? And so this is why we want to move away from the n-body wave function and to try to go in the direction of so-called one-particle approximation. So the idea is the following: is we have to solve this equation, and the term that is really annoying us is the one that I've highlighted in yellow. That's the electron-electron interaction. So if we can get rid of that, we come to assuming that there is no interaction. In that case, the equation simplifies quite a lot because you have something which is just the sum over something that is local for each of the particles, and you can do a separation of variables, and you can replace the n body wave function by a product of n one body wave functions, each of which need to satisfy the one electron Schrödinger equation that is here. Okay. So if we had that, in that case, the energy would simply be the sum of all the eigenvalues that we have here. So we would have that the energy of the ground state, so my notation here is that n is the number of particles, and the 0 refers to the ground state, is I'm going basically to occupy the lowest energy levels up to a certain level where I filled my n electrons, and in that case, that is the ground state of my system. Okay? So this is very convenient in terms of interpretation of saying this makes a connection to what Simo was presenting before. In photoemission, we try to get these eigenvalues En here. So this to obtain the band structure. The idea of photoemission, as we have seen, is that you shine some photon on the system of an electron, and then one of these electrons is excited, it gets some kinetic energy, and so there is one electron missing here, and so we move from a system of n electron to a system of n minus one electron. And so if we look at energy conservation, before, so on this side, we have the photon plus the system of n electron in their ground state, and we end up with an electron which is a kinetic energy and the system of n minus one electron in an excited state n, referring to the eigenvalue En here. And so if we write things together, we have that the difference between the kinetic energy and the energy of the incoming photon is given by the difference between the energies before and after the excitation, and that's basically the energy of the electron En that has been removed here. Okay, so we have a direct measure of the energies of the electrons by shining some electromagnetic radiation, extracting an electron, and just measuring the kinetic energy. Okay, that's a simplest picture, but that's the kind of idea they want to have. And in the same way, we can do inverse photoemission. That is, in that case, you send an electron with a given kinetic energy on the system, which is still in its ground state with an electron, and we end up with a system in which we have n plus one electron in an excited state n, related to the energy that we have here, and there is the emission of a photon. And again, if you do the energy conservation, you can see that the kinetic energy minus the photoemission energy is given by the difference between these two energies, and that's exactly the energy of the level that you are interested in. Okay, so given this, we would like to go in the direction of one particle systems, and there are two approaches. One is coming from chemistry, that's the wave function methods, and the idea here is really related to what I was showing you before, the idea to try to get a wave function that is as accurate as possible to try to get these eigenvalues. So the simplest approach that we have is the so-called R3 approximation, where we are assuming that the n electron wave function can be replaced by a product of one electron wave function, despite the fact that we still have some electron-electron interaction. So if there were no electron-electron interaction, in that case, it would be exactly as I was showing before. I could replace my n body wave function by a product of n one electron wave function. Here, I'm making the approximation that is the case, okay? If you do that and you enter that form of wave function in this equation and that you want to minimize it under constraint that we have these one electron wave function that are orthonormal, you just need to minimize this functional of the wave functions where we have the energy, and then we've introduced some Lagrange multipliers for the constraint that we have for the one electron wave. Okay, so if you do that, you end up with a Schrödinger equation, which is a one-body Schrödinger equation, as we were looking for. So that's a simple way to get to that. And to do that, I had to introduce the so-called Coulomb operator here that is given by this. And basically, you can think it about the probability of having an electron at a given position R prime, and then the Coulomb interaction of the electron that I'm considering with that other electron. okay? And so the eigenvalues that you get in this case are the R2 eigenvalues. And so you can write that these R2 eigenvalues are given by this formula here, and where we have introduced these terms here that can be computed in this way. So in that case, the total energy is not anymore just the sum of the eigenvalues, as I was showing before in the case of non-interacting electron. We have to correct for a double counting of these elements here. Okay, so you can do the math and do that. So the idea here is to kind of relate to what we were saying before. So this equation these equations that I was showing to you are very similar to the one that you may know, where we introduce the RT potential here, and the RT potential is given by the integral of the density divided by the distance r prime here, and the density is given by the sum over all the wave functions of the square modulus of these one electron wave function. So can you tell me the difference between the two equations actually? So between this one and this one. Very similar, but there is a slight difference. Just say it again.
Double counting?
No. There's no double counting.
During J interaction, there is a factor of half.
No, these two here, this here, look, the sum here goes over n. And that's the sum there as well. It's exactly the same. There's a small difference. It's not a double count.
The role of density.
Say it again.
The role of density is introduced.
Yes.
Is it a self-proportion?
So basically, indeed, that's something related to that. So the sum here goes over all n, whereas this one goes for all of them but the electron. Okay. So this one includes what is called the self-interaction. So the electron here, the density includes the electron that we are looking at, okay? And so this electron is interacting with itself, okay? Whereas here you don't have that, okay? Okay, and so again, you can write the total energy as the sum of the eigenvalues minus the correction, and this correction is the double count. Okay. Okay, so this formulation is of course a problem that if you want to solve, if you want to solve this, sorry, I have to go back to, here. If I want to solve this equation here, okay, I need to get the density. To get the density, I need the wave function. To get the wave function, I need to set this equation. And so the way we deal with that is doing self-consistency. That is that we start with a given density, we compute the R2 potential, from there we get the Hamiltonian, we solve, we get the wave function, we get the new density, and from this new density, we can iterate this loop here until we converge, okay? Now we know that the approximation that we have made to get to there is quite strong because we have assumed that the wave function is a product, so the many-body wave function is a product of wave functions, of one-body wave function, and that doesn't take into account the Pauli principle, okay, so that the electrons are fermions, and so the wave function should change side when we commute two electrons. So one way to go beyond that is to replace the wave function, rather than having a product, to replace it by a slated determinant. If you do this approximation that psi is equal to the slated determinant, this is the R3-Fock approximation. Okay? And in that case, you can write again minimization of a functional that depends on the energy minus some Lagrange multipliers that impose the constraint of orthonormalization of the wave function, the one-body wave function phi. And so, again, if you derive that equations, you can come directly to this. And so, if you haven't done it, I mean, I encourage you to do it to see where these terms are coming from. So compared to what we had before, so we had these J for the Coulomb operator, there's a new operator that is coming, and that's the exchange, so-called exchange operator. And this is a purely quantum term, basically. So you can see that compared to the Coulomb operator that we had here, it's just basically an exchange between these two wave functions and the name of the exchange. So again, you can get an expression for the eigenvalues where we introduce these two terms here, the J and the K's. And as a result, the total energy can be written by summing over all the eigenvalues minus a double counting again. Okay? And so finally, if we compare that to the R3 energy, correcting the one that we had for the R3 potential here, we introduce an exchange potential, which is written here, okay? And it's a non-local operator. So same question as before. Here, you want to see?
No, I just needed somebody from the room, but
So who's that?
I just needed Andrea to send these text messages. Actually, sorry.
Okay, so same question as before. Is there a difference between the two equations?
This time he has written also the index in the sum. So but pay attention, beware, because
So last time we had the self-interaction.
So this is self-interaction.
why?
Taking into account the electron which means so
So
Basically,
this is the sum over all the, so also n or not in the exchange operation? Sure. And so why it is self-interaction free if it has the same problem as the R3 approximation? Why R3 Fock is self-interaction free?
because maybe I consider it in R and I subtract in
yeah, it's exactly the same term. So if you come here and if you look at these two, then when you put m equals to m, they are exactly equal to 1, 1. Then so usually when you have this here, if you had put m equal to n, the difference between the two would be exactly the same. Okay. Okay, so in the R3 Fock approximation, we can try to make a connection also with respect to the picture that I was giving you of the eigenenergy. So if we remove an electron in the R3 Fock approximation, what happens is that we are going to remove one column here, so the one with phi n R1 and then so on here, and a line here in the determinant, and this gives us the wave function of the n-1 electron system in the excited state n, because I removed the line and the column. Okay. So when we do that, we obtain that the energy difference between the ground state of the n electron system and the energy of the n-1 system in the excited state n is exactly the eigenvalue of the R3 Fock system. Okay. And in the same way, if we add the one line and one column, so here you see that at the end, I've added the wave function for state small n, and here I have written an extra line here for the extra electron. The result for the difference between the two energies here, so the excited system of n+1 electron in their excited state n, and the energy of the ground state is the eigenvalue of the system. Okay. So when you do that for molecules, it works rather well. This is some work that Fabien Bonneval had done, and he compared the two. So when you look at the experimental ionization energy with respect to the calculated one, see that the agreement is very reasonable. Now, if you do the same, so that's for molecular for atoms. If you do the same for crystalline systems, so semiconductors here and insulators, you see that R3 Fock clearly overestimates the band gap that is measured experimentally. So, okay, well, you can say that the reason for that is probably because the wave function, the approximation that we took for the wave function is not accurate enough, okay? And so there's a number of methods that consist in trying to improve the quality of the wave function. So one way to do that is that we assume that the wave function was just one slated determinant, okay? We could go beyond that by taking more slated determinant that include excited states. So where you take you remove one electron, but you add another one in another excited state. So basically, you stay to a n electron system, but you take an electron from the valence band and you occupy it in the conduction band, and so you can create plenty of state determinant in that way. Okay, and if you are complete with respect to that, you have so what is called configuration interaction, which you do this linear combination. There's another way to do that, which is called a coupled cluster, and that takes advantage of the fact that if you write an exponential of the excitation operator, so the one that takes electron from the valence to the conduction band, if you do some kind of Taylor expansion, that is very similar to the linear combination. Okay, and now there is more and more. There's a code by Andreas Rignanese that is called CC4S because it's coupled cluster for solids. So these methods originally come from the chemistry community, and so they were mainly developed for molecules. But now these methods are being used more and more, even for the solids, especially the coupled cluster. So this one can be used for solids. You can do a DFT calculation, and then on top of that, you do a correction using coupled cluster. And so then there's another approach, which is called monoplacid. In that case, the n-electron wave function is obtained by means of perturbation theory in terms of the correlation potential. So in what I've presented so far, we've seen that there is the Gaussian term, there is the exchange term, which is called exact exchange, but there is still something missing, and everything that is missing, that is called correlation. And so you can do a perturbation theory in terms of that. And if you do that, you can see that the first order does not contribute to the electronic energy, and so you want to take higher order terms, and so you will see MP2 or MP3, which you take into account in the energy, and these you express them on a basis of doubly excited slated determinants. Okay, so these are the methods of the chemistry, which will not be seen here. So here we focus on density functional theory. And so the idea of density functional theory is to still consider our system of interacting electron with the electron-electron interaction here, and Oenberg and Co. that define that the density here, which is this integral over all but one of the variable of the product of these wave functions, okay? And Oenberg and Co. they demonstrated that this electronic density determines uniquely the potential that you have here. So if you have the density, so the solution of G and the phi, and you integrate in this way, then the external potential is fixed modulo constant. So how did they show that? There's first a lemma, okay? And let's consider that we have two local potentials, V1 and V2 of R. So the ground state wave function, which can or cannot be degenerate, but we can demonstrate, that's the idea of the lemma, that one wave function cannot be common to both these two potentials, except if the two potentials are equal to one another up to a constant. Okay. So the way that it's done is simply that, given that you have to write on the blackboard, because I didn't do it here, I'm going to do the formula derivation, but basically, if you have, let's say, HV1, which is so the kinetic energy plus 1, okay? And then we have H2, which is equal to the kinetic energy plus V2. Okay? So if you have something which is the same wave function, okay, H psi is equal to V1 psi, and then we have HV2, which is equal to this one psi here. If you make the difference between the two, you're just left with what is written here. You have that the difference in the potentials here, plus the difference in energy, times the wave function should be equal to 0. And that should be true everywhere. Okay? So that means that in practice, if you fix the position for all the indices but 1, so from 2 to n, then you obtain that the difference V1 of the remaining variable R1 and the V2 at the same R1 must be a constant in space because the wave function is not 0, it is 0. Okay? But that's the lemma. So if you have two different potentials that are different by more than a constant, they cannot have the same wave function as their ground state. Okay? Don't hesitate to interrupt me if there is any question.
Is it true only for the non-degenerate state? Because you cannot do that in the degenerate state. That would be
I think that's true for any case. But then here we say, so I don't see what it would change here actually, the fact that it's degenerate. If it's the same wave function. I mean, it's the same wave function between these two. So even if it's degenerate, I don't see where it changes.
because sometimes this type of things that done through the non-degenerate states.
The dilemma here, I mean, in what I've done here, there is nothing that requires that it's not degenerate. The only thing is that it has to be the same wave function. Okay. Okay, so now that we have this lemma, let's take a psi1, which is the or one of the, so it could be a degenerate one, a ground state wave function for my first Hamiltonian, HG1, okay? And then psi2 is the or one of the ground state wave function of my second, okay? Because of the variational principle, we have that E1 here, which is psi1, HV1, psi1, is going to be the smallest value that you can get for whatever wave function that you put here when you take HV1 here. And and E2, which is this one, is going to be the smallest wave value that you can get for whatever wave function you put here. Okay, so in particular, we have that if I put psi2 in the first one, we have that psi1, HV1, psi1 is strictly smaller than this one. Okay, because psi2 is not the ground state of the other one. Okay, they are different. So I can rewrite this one here, okay, as, this one here, psi2. I can write it psi2, HV1, psi2. I can write it as psi2, HV2, psi2. And then I just do the HV1 here minus what I just added before, okay? And when you look at this one here, that's basically simply the difference in the potential times the density, okay, that I integrate over the whole space. Okay, so this term here is E2 plus something, okay? And it's indeed bigger than the E1. So I can write that E1, so if I go back here, this one here, E1, is smaller than this one here, which is E2 plus the difference. And if I do the same by interchanging 2 and 1, I will get that E2 is smaller than E1 minus plus the difference that you have here. Okay? And now if I do the difference between these two, I have 0. It's going to be equal to, okay, we have a change of sign here in the potential, so you have that V2 minus V1 times this difference here. Okay? And so if we have that the density N1 is equal to N2, in that case, we would have 0 smaller than 0 everywhere, and that obviously doesn't. Okay? So that means that if we have two different densities, they need to have two different potential gluons. Okay? So basically, the main thing of Owen-Cohen theorem is to prove that once we have the knowledge of the ground state density, the external potential is fixed to a ground state. Okay? And as a result of that, anything that is potential is this can be written formally as a functional of the ground state density. So once you have the density, you have the external potential. We don't know what it is, but we can write it formally, and it is fixed up to a constant that we usually fix by some limit at the infinity or something like that, okay? And so this is why everything is going to be written as a function of the density, and the acronym that's the differential theory, okay? So furthermore, once you have the external potential, as I was mentioning, the total energy, for instance, can be written formally again as a function of the density. We just need to take the expectation value of the Hamiltonian that is there, okay? It is uniquely defined by specifying the external potential and the expectation values that we have there gives the total energy. Okay. So what we have to do in the end, thanks to the variational principle, we know that this here is minimum in the ground state, okay? So if we find the density that leads to the wave functions that minimize the ground state, we will have minimized everything. And so formally, we can split this Hamiltonian into the kinetic energy, the Coulomb interaction term, and then the integral here over the external potential. So basically, this is another functional of the density, and this one is one that we know because the external potential is given, and so we can obtain an explicit form for this one. But for this one, we still don't have any explicit function, so it's a functional of the density, which is universal, but we don't know it. Okay, so there is actually field research in which people are trying to obtain the best approximation for this f of n, okay? And for instance, for the kinetic energy, they take the so-called Thomas Fermi approach, where we know that there are some stuff that is missing, but they try to get a more and more accurate version of this functional. The problem of that is that this piece is rather big, and so other approaches are needed to do a better job, because it's difficult to get a reasonable approximation for that. So Kohn and Sham, they tried to get some more reasonable approximation. They tried to establish a connection between a system of non-interacting electron with the same electronic density. So they want to find something for this functional here, starting from a functional where this is the kinetic energy of non-interacting electron. Okay, so this is a known functional. And furthermore, they said, okay, in this thing here, there must be something that looks like the R term, which is also a known functional of the density. So out of this, they took two pieces that are known, this one for the kinetic energy of the interacting electron and the R term. And so they define the remaining as the exchange correlation energy functional. So basically out of this Fn, I remove my kinetic energy of non-interacting electron, I remove the R3 energy for non-interacting electron, and this, everything that remains, that's this exchange correlation functional energy. The advantage compared to trying to get directly the functional for f of n is that this one is much smaller, and so even if we make small errors on that, that works reasonably well. Okay? So if this functional is known, then we can simply write that the total energy, which is a function of the density, is the term that is related to the kinetic energy of non-interacting electrons. This integral of the density times the external potential, the R2 term plus the term that we don't know, and we have to minimize that one under the constraint of a fixed number of electrons. Okay? So in this exchange correlation potential, but by the way, what is there compared to what we were doing before? So if you think about what we have done about the wave function methods, okay, the reason why it's called exchange correlation method is that because we know that there is some exact exchange in there in principle, okay? And then there is the correlation, okay? And the correlation there, is it the same as the one that we had before in what we, when we were dealing with perturbation theory in the molar placid term, for instance?
It's not, because here the key correlation comes by considering Born-Oppenheimer approximation.
That was the same in both cases. The Born-Oppenheimer was the same in both cases. But in the other case, so we were assuming that the wave function was slated determinant, okay? And then we found that there was exact exchange, and we said, okay, there's still something missing, and this we call it the correlation energy. So here, there's again correlation that appears, okay, but there is a slight difference.
It's the kinetic energy part?
Exactly. So the kinetic energy part that you have here is the one of non-interacting electrons. Whereas in the other case, we were still considering the electrons correctly. Okay, so this correlation part here includes not only the correlation effects that we've seen in our fog, but it also includes what is missing in these terms, to get the kinetic energy of interacting energy. Okay?
And it contains also change.
Yeah.
In a local form.
Okay. Okay, so we have to minimize this energy with respect to the density, okay, under the constraint that the integral of the density is the number of electrons. So we can do that by introducing a Lagrange multiplier lambda here and deriving this functional respect to the density. And so if you write formally the derivative, the functional derivative of this expression here, you get this term here, you get the external potential, you get the R2 potential, and you get this other thing that, because the other ones are potentials, is going to be called a potential as well. And so we can formally write things as if there was a potential, the Kohn-Sham potential, which is the sum of the external potential plus the R2 potential, and then this term here, which we'll label the exchange coordination potential, okay? And formally, minimizing the total energy here under this constraint is exactly equivalent to solving this equation, this Schrödinger equation with one electron, with the density given by this. And again, there's a self-consistency problem because the Kohn-Sham potential includes the density. Okay?
I have a question about when it comes to laser cameras, because from the derivation we see that these are Lagrange.
Exactly. I was going to come to that, but
What is the physical extent of like considering it the energies of the orbitals? Like
there's no formal justification, and this is the reason why there is a problem with the band gap. The only one that is justified is the HOMO. The HOMO is correct. The other ones are Lagrange multiplier, as you were. I think it's my next slide. No.
So the slides Gian-Marco has shown about antifoc, showing that the excitation energies as measured in photoemission experiment can be described by artifoc eigenvalues. That demonstration does not hold for the case of density functional theory. So the demonstration means that there is a Koopman theorem for artifoc eigenvalues, and this does not hold for the case of density functional theory.
I'm going to conclude that. Okay, so once we have reached self-consistency in the Schrödinger one electron equation, assuming that we know the exchange correlation functional, in that case, the electronic density is the electronic density of the ground state, and so the total energy is the exact one for the ground state. Okay? And as we were pointing, so the wave functions and the eigenenergies correspond to a fictitious set of independent electrons. So in principle, they do not correspond to any exact quantity. Yeah, so solving the Schrödinger, the Kohn-Sham Hamiltonian is strictly equivalent to minimizing this function of the wave function here, okay, under the constraint that the wave functions are orderly. So now we still have the problem that we don't know what this exchange correlation energy, and I'll come back to it again later on. We still have the problem that we don't know this exchange correlation functional. And the good point of the paper of Kohn and Sham was that at the same time, so they derived this Kohn-Sham equation, but they also made a very reasonable approximation about this exchange correlation functional. So basically, first of all, what we do is that we write formally this exchange correlation functional of the density as an integral over the density times a density of exchange correlation, okay? And so Kohn and Sham, they came with the idea that we can make a reasonable approximation for this exchange correlation density. And they said that rather than depending, so formally, this exchange correlation here, it depends on the density everywhere. Okay? So they made the approximation that in fact, this exchange correlation energy only depends on the density at the point where I'm considering it, okay? And furthermore, they have assumed that it was the one of an homogeneous electron gas, for which there is a formal formula for the exchange, an analytic formula for the exchange. So you can write exactly that for the exchange of an homogeneous electron gas, the functional form of the exchange energy is written in this way. Okay? And for the correlation part, they did some number of numerical calculation, and then they did, for instance, quantum Monte Carlo, and they obtained some formula to get it. Okay? And it kind of worked. So for instance, what does it mean that it kind of worked? Is that if you take this example here of hafnium and zircon, so zircon is something that sometimes you will see in jewelry because it looks like diamond, but it's not diamond, so it's way cheaper. And so it's a body-centered tetragonal unit cell. So there is a primitive cell with two formula units of MSAO4, M being hafnium or zirconium. So you can see that as alternating SaO4 tetrahedra and MO8 units along the 001 direction. So the MO8 unit consists of 4 oxygen that are closer to the zirconium and other 4 ones that are further away. And each of the oxygen atom you can see here, so the corner of my polyhedra here are oxygen atoms. So they are connected to 1 silicon in the tetrahedron and 2 of the metals here. So they have 3 bonds. Okay. So this is a system. And for this system, when you compare theory and experiment, you can see that the agreement in terms of geometry is really very nice. We typically have 1 or 2% on the lattice parameters and all structural properties. Okay. So this is very interesting. And this is why this approximation has been popular for a long time. But there are a number of cases where it doesn't work. So for instance, the hydrogen bond, it is well known that LDA has a problem with that. And so people came with other approximation, one of which is the so-called generalized gradient approximation that basically says that this exchange correlation here depends not only on the density at the point that we're considering, but also of its gradient, hence the name generalized gradient approximation. Okay? In this case, there is no analytic formula as in the case of LDA for the homogeneous electron gas, but other analytic expressions have been derived and proposed, so that you have an explicit formula to compute this exchange correlation. And so there is a number of flavors of the GGA that have been popular in the past. So you probably have all heard about PBE, so that's Purdue, Bergen, and all the right one formulation. There is an expression that is more accurate for solids, PBE sol, but in the past, so you see there is the numbers that you see there is the date, so that's 1986, 1981 for Purdue and Wang in both cases. And so there's different methods. Then there is another kind of functional, which tries to say, okay, we know that there is some exact exchange in there, so let's try to derive an exact expression for that and to put it in there and just remain with what is missing, okay? There is also methods that, because we were pointing that there may be problems of self-interaction, are trying to correct that, to remove this self-interaction. And finally, the most popular ones at the moment is the hybrid functionals that include a fraction of this exact exchange and another part, which is one of the normal GGAs. Okay? And now there is also meta GGAs where you include the density of kinetic energy, the density of kinetic energy as a complement to the other functional, and that one is way less demanding than the hybrid one. So if you looked in the past, all the things that I mentioned there, so this is an old paper from 2003, and was showing the number of citations, so the papers that are cited more than 1,000 times at the time, in all physical review, okay? And you can see that out of all those, many of them are related to density functional theory. You have this Bonensham paper, Warren Barrington paper. There was this paper about self-interaction correction, and there was this one about the correlation part that I mentioned before, and some other that also related to density functional theory. So our field is kind of important, and even if we take a an older paper, so that was done in 10 years ago, in which they were reporting the paper that are cited the most. And so they were taking a sheet of paper to represent each of the papers. So you just take the cover of each of these papers and you stack all the papers that have been published so far, I mean, till 2014. And till 2014, they were already, when you stack for each paper 1 page, you reached the 8, that is something like almost 5,000 meters. Okay, and if you look at this paper, at this picture here, you see that up to here, all these papers, they have never been cited. Okay, so then from here to here, they've been cited from 1 to 9 times. Okay, thank you very much. And then from here to almost the top, so from here to here, that's between 10 and 100 times, and more than 100 times is the very top. But then if you look at the top 100 papers most cited, you see that there's a bunch of those that are related to density functional theory. Actually, there's many of those that are related to the functionals, because finding good functional is something that is very important. Okay? And there's obviously some about the papers. This is the paper about VASP. This is about the K-point sampling. This one is about VASP also. So there's a number of citations.
But there should be one in the top 10, no?
In the top 10, yeah, 7 and 8.
Okay. And
That's blip function.
but there was
Chemistry.
one about the functional. It was a really, really high citation about the. Are they the first 10?
Yeah, from 2014. Maybe there's been
No. There are 2 different lists. The list you have shown in the previous slide is only physical review paper
No.
cited by
This
physics.
one.
These are papers cited by everything, so also by chemistry papers.
Yeah.
So the LIP
chemistry
is mostly cited
by
by
chemistry.
chemists.
Yeah, I remember there was one with hundreds of thousands of citations, but something about the Colle Salvetti, no? Okay, I will check, but there
Yeah,
was
check.
really a lot of citations, yes.
Okay, so in principle, this if we solve this one, we can compute all the ground state properties, okay? And as we discussed already, and as you were pointing right correctly, there is no formal reason to interpret the Kohn-Sham eigenenergies as something else than just the Lagrange multipliers, okay? But still, people have used and continue to use these electronic density functional theory band structures and compare them to experimental data. And in many cases, it works quite well, apart from the band gap that is systematically underestimated, okay? And this problem is related to the existence of a discontinuity in the derivative of the exchange correlation potential function, okay? So in practice, if you do a plot of the experimental band gap versus the calculated one, you see that we are systematically underestimating here. And one of the reasons why I guess you are here is about using the many-body perturbation theory to go beyond this problem, okay? So formally, if we want to define things, the difference between the energy of the ground states energy of an n+1 system of electrons and the ground state of the system of n electron, that is the minimum energy that is needed to add 1 electron to the system, and this is called the electron affinity. Okay, so the electron affinity is En+1 in the ground state minus En in the ground state, and then this other difference is the energy that you need to remove 1 electron to the system. So you go from a system of n electron to a system of n-1 electron in their ground state. And so this difference is the minimum energy that you need to do that. And it's called the ionization energy, okay? So in practice, can be shown that the ionization energy is smaller or equal to the electron affinity. And so we can define a quantity that is electron affinity minus the ionization energy that is given formally by this difference here. So basically you have En+1, 0 plus En minus 1, 0, minus twice the energy of the En 0. And this defines a quantity that is positive that will note Eg. And you can show that in atomic or molecular systems, we have that this inequality is a strict inequality. So, and this is going to be the energy of the HOMO, and this is going to be the energy of the LUMO. Whereas in a solid, we can define a chemical potential that is such that it's comprised between the ionization energy and the electron affinity. And if you take the thermodynamic limit of V going to infinity while keeping the number of particles divided by the volume as a constant, we can distinguish two cases: the metallic system in which this value is going to be equal to 0 because both the ionization energy and the electron affinity are equal to the potential, the chemical potential, and an insulating system in which the gap here is going to be bigger than 0 because we have a strict inequality between the ionization energy, the chemical potential, and the energy. Okay. And so, as I was mentioning, there is a problem of discontinuity, and I will define this more precisely. If we extend the DFT to cases where you have a non-integer number of electrons, that's weird, but we can still do that from a mathematical point of view. We introduce a fractional number of electrons, so where n is an integer, and then a delta, which is comprised between 0 and 1, okay? The density of the system of n plus delta electron, we define it as a linear combination between the case of n electron and n plus 1 electron, okay? In the same way, the energy of that system of n plus delta electron is a linear combination between the two, okay? And in fact, when you do this, you can see that the derivative for n smaller than a number of electrons that is smaller than n, so n minus delta, that will give you the ionization energy simply by putting an En and En minus 1 here. And the other one is when you take the derivative for n plus delta, you get the electron affinity because that's En and En plus 1 there, okay? And so you can see that the quantity that we had before here, this quantity that we've defined here, the Eg, which is the difference between the two, it is related to the change in the derivative that we have between these two things, on the left and on the right, okay? So in principle, derivative on the left and on the right, they should be different, and this difference should be the gap. So when you do something like, if we had an exact DFT, it should look like this. So where we have a linearity between the energy at E minus 1 and En, and then En at En plus 1, okay, that would be exact. If you do a typical LDA and GGA, it's going to be convex in this way, okay? And so the derivative on the left and on the right, they may have a discontinuity, but it's not the exact one, okay? And if you go to Hartree-Fock, the concavity is on the other side. And as a result, this is why when you do a mix of the two, when you do some hybrid, you get something which is closer to the linear. And as Valerio was pointing, there is a branch of the research in our field that's trying to get Koopmans compliant with exchange correlation functional that kind of respect this piecewise linearity of the energy. Okay? So this brings me to isotope screening. How am I doing this thing? Ancora. Okay, so this field of density functional theory has been there for quite a long time, and so it has reached a level of maturity that is such that now it is possible to screen for materials with given properties. So the idea is the following. So when, for instance, Edison was searching for the filament of the bulb lamp, he tested something like 3,000 materials. So, you know, he made the experiments of trying one after the other, including the ears of his assistant. And in the end, the material that he found was not what we ended up using for a long time, which is tungsten. He didn't find tungsten simply because he didn't try tungsten, okay? So when you do trial and error, you just can get the best out of what you try, okay? So the idea of the high throughput screening is to try to do better than Edison, so to go rather than a few thousand, but to go to hundreds of thousands of compounds. And rather than making the tests, we actually compute different properties with DFT. And based on the application that we have in mind, we set up a number of properties that we can compute one after the other and try to find the materials that meet all the requirements in terms of the different properties that we have in mind for the application, okay? So if you've seen from this small animation, there's a number of materials that end up in the dumpster here, and I'll come back to that. But out of those, there is something like 10 to 100 of those that make it through the filter that we did by computing different properties from density functional theory or even beyond, because at the end here, so you will see that doing GW calculation can be very demanding, but when you have a funnel like this one here, at the end you have a limited number, and I will give you an example afterwards. You have a limited number of materials, and then you can afford doing more involved calculation. That's the whole idea of this funnel, is to do easy calculation at the top, DFT, and when you go further down with simple functionals, and then when you go further down, you can do something which is more evolved. I will give you an example. And then if we did a good job, in principle, our colleague can synthesize the material and verify that what we have done is correct. To do these kind of things, there are two things that are important. That's the high throughput, and so there is developing workflows to do all these calculations automatically. Actually, next year in March 25, there's going to be a tutorial here that has already been accepted about workflows for doing this kind of calculation. And the other thing is that all the data that we put in the dumpster, they are not lost. It's important to do data mining and machine learning, which is kind of trendy nowadays. So just to give you an example, if you are looking for Earth-abundant solar absorbers, okay? So the solar absorber, that's the layer that's basically creating the electron pair. So the one that is used the most often at the moment is silicon. And what you want is to develop alternatives because, so you would like to have things that are based on the highly absorbing semiconductors. So the silicon has an indirect band gap, and that can be a problem. And also you would like to have sort of thinner materials in such a way that you can have mechanical flexibility and a smaller carbon footprint, okay? The drawback of the materials that have been tested so far is that they have a problem in terms of scarcity of the elements that you have there. There's often indium, gallium, tellurium there, or sometimes toxicity of the elements, so lead or cadmium can be used, cadmium telluride, for instance. And there is also long-term stability problem. For the moment, the hype is using halide perovskites, and these halide perovskites have problems in terms of stability. And so we're still looking for Earth-abundant solar absorbers that have high efficiency, either as thin films or in tandem cells being that you have one material at the top with a small gap, and then another one down with a larger gap. So there's been a number of high throughput screening studies, so these funnel approaches that were based mainly on bulk properties. So you look for a material that has a good band gap because there is an optimal band gap defined by the Shock requires a limit in terms of maximizing the efficiency. You want to have good effective masses, meaning low effective masses, because you want to have carriers that are kind of fast, and you want to have a good optical absorption. But in fact, when you look at solar absorber, its efficiency is mainly driven by the carrier lifetime. So you can have good effective mass, a good band gap, but if your carrier recombine, that's a problem. So typically what you want is that when you create an electron hole pair, you want to separate them and to collect them at the different cathodes of the photovoltaic cells. What you really want to avoid is to have a recombination of the electron. Okay? And so one of the reasons why you have this kind of recombination is the so-called Shockley-Reed-Hall non-radiative process, whereby the charge carriers, they recombine by releasing phonons instead of phonons. And these involve traps, as I will show you. So typically, if you have the conduction band and you have created an electron hole pair, okay, they can recombine in a radiative way by emitting photons, okay? And so this is not something that is very strong in typical material. In contrast, if you have traps, and in particular, as you will see, if you have traps in the middle of the band gap, rather than making a big transition, you can have intermediate transition, and the energy that is released for each of these small transitions is smaller than what is needed to release a photon. You just can release this energy with a phonon. Okay, you can do these kind of things. And then other kinds of recombination process, that's non-radiative Auger recombination, and these involve the emission of particles, electrons, or okay. And again, because as you had seen before, sorry, for these ones, I'm sorry, I'm going to have to go through my animation again. Okay, the non-radiative Auger is less likely because it involves more particles to be in the neighborhood. Whereas these ones, the Shockley-Reed or recombination process, they are really driven by the position of the defect in the band gap. So if you have a shallow defect that is close to the band edges, you've changed nothing compared to the radiative process. And it also depends on the captured cross-section. So the position that is the most detrimental is when the electrons are in the middle of the gap, okay? So the deep defects are really what is unknown. So we have developed a model in which we first assumed that the cross-section was kind of constant because it's difficult to compute, okay? And so we then computed the position of the defect, and from there we could get an idea of the radiative lifetime of the pairs, the carriers, in different kinds of materials, and we compared the efficiency that we got out of this model that took the position of the levels into account. We compared that to the experimental efficiency. So you have here the experimental efficiency, the theoretical efficiency. So these materials are considered to be not very good experimentally. These are considered to be very good. And you see that when we compare our prediction to what has been done experimentally, the results are kind of nice. There is little number. So here there is no false positive, and here there is a number of false negative, but it's not so important. So the typical funnel that you would have to do these kind of things, as you can see, is consider, let's say, 8,000 materials. So these were all based on copper, okay? And we compute a number of properties, the thermal stability, the band gap, the all effective masses. And based on that, we reduce the number of materials that meet the requirement here, okay? So as you can see, the band gap is computed the second time here. And the difference is that in the first part, the band gap was computed with PBE, so the color blue here on the box is refers to the functional, whereas here we have a better functional HSE, which is an hybrid, okay? And for different things, you can compute them several times. So for instance, here, we look at the position of the point defects, computing it by doing a PBE corrected by HSE, and then further away, we do the calculation, exact calculation with HSE, but with a reduced number of materials. You see that by reducing the number of materials when you go down the funnel, you can do more advanced calculation, and as a result, you are more accurate. And so you can propose to your experimental colleague better results. And you see that at the end, we can even do advanced calculation of the capture coefficient that I told you in the beginning, we kept it constant, okay, once we have a limited number of materials. So out of that, we found 6 materials that belong to 2 categories, some which were truly defect tolerant, so no defect in the band gap, and some other that had a defect in the band gap, but they had a large formation energy, so their concentration would be small, and so they will not affect the quality and the efficiency of the material. So once you have that, you can take other criteria into account, so you can try to make sure that the elements are earth abundant, and that they are not concentrated in a few geographical region. You know, if they are produced all in China, it can be a problem. And so there is this HHI index that indicates where the material is produced, right? So the lower the HHI index, the better. It means that you have something that is produced all over the world. And then there is another indicator, which is called the materials componentality that you have colored here. That's something that indicates when you extract some elements from the ground, okay, they sometimes lead to the production of another element. So if you extract, I don't know, copper, maybe there's another one that is coming with it. And that second one is a byproduct, so it's cheaper compared to the first one. And so it's always nice to have this kind of complementarity. Okay? And so when you look at that, you have a number of interesting materials here. So this one and this one have a low HHI index, and they have a good materials complementarity. So we extended this to 40,000 materials. So you see that because we can do this calculation, we can produce more. And this one actually, has been synthesized. We studied it, and so our experimental colleagues synthesized it, and they found that it had indeed the good properties that we had predicted. So you see that by taking this approach, you can help the experimentalists discover new materials. So the density functional theory can really help. So it can be applied to a number of things. So I just listed a few number of papers here where we used that to discover transparent conducting materials, electrolyte, high refractive index and wide bandgap materials, high Curie temperature ferromagnetic, thermoelectrics, and multiferroids. Okay? If you have questions, don't hesitate to come to discuss with me. I can show some of the things here. The other thing that I wanted to show is that, as we have seen, when you have these funnels, there is a number of materials that go into the dumpster. Luckily, what has appeared is that people didn't throw the materials in the dumpster. They actually created databases that are now available online. And so whenever they compute properties, new properties, you can find them in these different databases that maybe you've heard of, Materials Project, Nomad, Materials Cloud, QMD, Flow, and so on. I'd like to here underline, as Sarah was pointing, the importance of SECAM here. So when this started, all these different databases, they had a different APIs. So the way in which you would interrogate the different databases, it was completely different. So that was really annoying from a user point of view. And so we managed to gather here at SECAM, first at the Lawrence Center in the Netherlands, but then most of the time at the SECAM here, and with a strong support from the SECAM, we gathered the developers of these different databases, and they produced a common API. So there's a specification of this common API, and there are some tools that you can use to use this API. And now it is possible to query all these databases with the same query. Okay, so you make the same query, and you can gather the data from all these databases. And this is very interesting if you think about what we are experiencing in our field, where we moved from the so-called first paradigm of science, which is the empirical science that I was trying to explain to you with Edison testing 3,000 materials, then we developing some theoretical knowledge and then doing simulation. And now we are entered into the era of data-driven science, whereby we use all the data that we've produced to make predictions that are faster than the FT. Okay, with that, I'm moving to the last part of my talk, and let me just drink a bit. Are there any questions up to now? Yes.
How to do quantified calculations?
How to do 25 calculation? You use what is called workflows I was mentioning. So for AbiNit, we have something that is called AbiPy. But
Okay, fine.
AbiPy is a starting box, okay? But then there are other tools. So I mean, so here in Lausanne, for instance, they're developing something called AIDA that you may have heard of. And the other one that we are developing by participating to development is called Automate. So Automate makes it easier to run calculation automatically. AIDA makes it easier to run calculation automatically. And so to do that, you need to define workflows, and there are different tools to do that. Okay? Yes?
I have a question on functionals.
Yes.
Is the LDA the only one that is parameter free?
No.
So you have GGA methods which are parameter free, where there is no fit on.
I mean, people have come with parameter there is parameter, then you can impose some rules to get the parameters. So all of them, they have a number of parameters, but so when you say parameter free, I mean, if we go back to the formula of DFT, there is some parameter.
Even fitting on that.
But LDA is fitted on QMC for the correlation part of the homogeneous. So it's just a matter of how you define things. There's always some parameters. So now the hybrid, if that's what you have in mind, they typically have a parameter that you can tune and that you change from one material to another. As long as you have something that is general and not material dependent, you can say that it's parameter free. Okay. And even now, there's some hybrids that are being developed by Leo Kronig and Jeff Neaton, where they take into account the dielectric function of the material, to define the parameters. The parameters, you can define them from physical properties. Okay. Okay, so you will be, this afternoon, you will be using Init for doing a DFT calculation.
Let's hope, because there is a cluster urgent maintenance because it's done.
Okay.
Let's see, let's see.
Let's see what happens. So maybe you will be doing Abinit on a sheet of paper. But okay, so Abinit is a package that is aimed at doing DFT calculation using pseudopotentials and plane wave basis sets. So you will simply get the forces and the stress, and so you can relax the geometry. You will be using Abinit also later on in the week to do many body perturbation theory, so a GW and beta plate calculation. And it's an open source code that favors the development, and so anyone that is interested can join the collaboration and contribute. There are other codes that are open source also, but here we will be using Abinit. So the first thing that you will have to do is to describe the structure of the system to be investigated. So this afternoon you will have a number of tutorials, but I'm still giving you some information about the input that you will have to write or to use. Okay, so the first thing is to define the structure, and defining the structure is describing the primitive cell, and the primitive cell is typically defined once you give 3 lattice vectors. Once you have 3 lattice vectors and you define the unit cell, the whole crystal is defined. So sorry for that. So the unit cell is typically defined by 3 lengths, A1, A2, and A3, and 3 angles, alpha 1, alpha 2, and alpha 3, which define the 3 vectors, A1, A2, and A3, okay? And you have the example of the triclinic system in which the 3 different lengths are all different, and the 3 angles are all different. And in the contrast, you have the cubic system in which you have the 3 lengths which are equal, and the 3 angles that are equal to 90 degrees, okay? So you can come back to the asymmetric unit cell, and this can be sometimes interesting. So that means that you just need to define a limited part of the unit cell, and then by applying the symmetry, you recover the complete unit cell. And then thanks to the lattice vector, you recover the complete crystal. So in Abinit, there is several ways to define the properties that you have there. The first one is that basically, internally, the variable that is used is this R prime D that depends on 2 indices that basically describes the 3 vectors that I was telling you before. So A1, A2, and A3. So the I here is the index for A1, A2, and A3, and the J is the 3 different coordinates of X, Y, Z. Okay, and so the way you specify these, okay, is thanks to this R prime JI, which you can either scale by line or by column, okay? So for instance here, if you have a face-centered orthorhombic, you see that face-centered, you typically have to take something which is 0, 1/2, 1/2, 1/2, 0, 1/2, 1/2, 1/2, 0 as the 3 vectors. These are the vectors that go to the center of the faces, okay? But then, given that it's tetragonal in this case, that it's orthorhombic, in this case, then you have to multiply the different column here by a different number. So this number multiplies this column, this number multiplies this column, and this multiplies this column, okay? In the case of an hexagonal system, you prefer to multiply by the line, because then you define these 2 vectors, which are square root of 3 divided by 2, 1/2, 0, minus square root of 3 divided by 2, 1/2, 0, okay? And these 2 have the same length, so you multiply both of them in line by this A cell parameter. And then the third one is in the C direction, and it's multiplied also by A cell. So you see that you have a lot of flexibility to define these vectors, okay? Sometimes it is more interesting to define the vectors not based on their coordinates, but by giving their lengths, A cell, and the angles, angdeg here. So the brown here indicates the name of variables in Abinit. Okay, so you can define the same as this one by saying that it's 3 vectors that have lengths of 9.5 and then 10 for the last one, and the angles are 120, 90, 90. okay? This is very convenient, for instance, if you have a trigonal system, because in that case, you have the same length for the 3 and the same angle, which is, for instance, 48 degrees here. If you would have to give the coordinates of the vector, it would be a bit more cumbersome to do, okay? So the other thing that is interesting in Abilit is the symmetries. So you can either give them yourself, or the code finds them for you. So adopting what is called the SATES notation, that basically consists of this thing here, which is a 3x3 orthogonal matrix, okay, which you can specify in Abilit with CMRL, we will see that. And then a vector that describes the translation of the symmetry, okay, and this vector is typically smaller than the vectors of the unit cell, and the variable for that in Abilit is T nonce. Okay, I'm sorry for that. Yeah, let me correct it right away, because otherwise you won't see anything. Oops. Here you go. There you go. So how does it work? When you apply a given symmetry operation to the position tau of an atom, you have to apply the matrix, multiply the matrix by the vector. Okay, so that's a rotation, a mirror plane, or whatsoever. And then you have a translation if it's an helicoidal axis or a glide plane. Okay. And so the position that you get is a different atom, okay, which can or cannot be in the same unit cell, or you have to bring it from another unit cell. You do an operation, a symmetry operation, it can go outside the primitive cell, and then you can bring it back to the unit cell. Okay. So to specify the content of the unit cell, you have to specify the number of atoms that you have in the unit cell. That's the variable n atom. And then you have the reduced coordinates that you can specify, x red. If you prefer, you can specify the Cartesian coordinates, either in Bohr, in that case you have to use the variable x cart, or x angst if you want to use it. Then you need to specify what are the kind of atoms that you have in the unit cell. And so you label them 1, 2, 3, then you will use a pseudo-potential to define each of those. And then you can specify the space group. If you know it in advance, you just specify the space group. And in that case, you just need to specify the position in the reduced, the asymmetric unit cell. And this is why you can define the number of atoms in that reduced unit cell. You can specify the number of symmetries. And if you want, you can specify each of the symmetries. The other way around is to just specify the position and the code finds them for you. Okay, just as an example here, if we take a cubic zirconia, which is an F m minus 3m, so it's an FCC. Okay, it's a cubic face-centered with the zirconia that occupy the corner and the center of the faces, and the oxygen that occupy these sides here, which are the Wyckoff centers 8C. Okay, so there's 8 equivalent positions. So in Abilit, again, let me correct it right away. Okay, so we specify simply. I changed my slide yesterday, and as a result, the font changed, and so everything was messed up. Anyway, so you see that here there is 3 atoms in the unit cell. So the primitive unit cell is the one that is in green. You see the one that goes from the corner to the center of the face, corner to the center of the face, and the corner and the center of the face. And so you have the one that is represented here in green. Okay, it includes 3 atoms. So we specify the lattice parameters. It's an FCC, so it's 0, 1/2, 1/2, 1/2, 0, 1/2, 1/2, 1/2, 0. The length of the parameters, and see that you can add a label here to say that the units that I'm using here is angstrom. By default, it's atomic units, but if you want angstrom, you just put angst after the variable. Okay, there is 2 types of atoms. There is the zirconia, which is the 1, and then the oxygen, which are the 2. And the position is 0, 0, 0 for this one, and then 1/4, 1/4, 1/4, and 3/4, 3/4, 3/4, or -1/4, -1/4, -1/4. If you enter that as an input to Abilit, it will, and sorry for all that, I'm going to change my slide online also, because otherwise it's going to be a mess for you. I'm sorry. Here you go. So if you enter that input to Abinit, in the output file, you will find that the code has found that it's FM-3M, that is the space group 225, and it will give you the list of all the symmetries, okay? And so you have the identity here, for instance, so 1000, 010, and 001. This is an inversion symmetry, okay? And you can visualize them with different tools. So for instance, there is, sorry, all these things, what are it? Okay. So alternatively, you can, and again, there is a bit that is missing. I'll change that afterwards. So in this case, what I'm trying to show is that you can say to the code that the space group is 225, and that the number of atoms in the reduced cell, the asymmetric cell, is only 2, and you just need to specify these 2, which are just the 2 positions that you had here, 0, 0, 0, and 1/4, 1/4, 1/4. These are the Wyckoff positions, okay? And again, everything is perfect. And then if you go to silicon, as an example, so that's again an FCC, but in this case, the space group is 227, okay? So in this case, we can again specify that there is 2 atoms in the unit cell. We give the lattice parameters. It's again an FCC with 0, 1/2, 1/2, 1/2, 0, 1/2, and 1/2, 1/2, 0. There's 2 atoms in the unit cell, one in 1/8, 1/8, 1/8, and the other one in 7/8, 7/8, 7/8, okay? And the code will find that it's the space group 227, and it will give you all the symmetries. In this case, some of them are symmetric. There is no translation associated to that. And sometimes there is some translation associated to it. But if you want, you can also specify it by yourself. As I mentioned in the beginning, we'll be using, oh shit, I'm sorry. We'll be using the plane wave basis set. Okay, and the idea behind this plane wave basis set is that we have block theorem that holds. That basically the wave function is given by the product of a plane wave by a function that has the periodicity of the lattice. Okay, and we have the g vectors that are defined by this equation that EIGR, where R are the lattice vectors of the original systems. They are equal to 1, and as a result, you can develop the periodic part of the wave function as a sum over these g vectors of some coefficients times the plane wave. And these coefficients can be obtained by doing a Fourier transform, and as a result, the wave function is simply a sum over these g vectors of these coefficients times the EIK plus J of R. Okay, where K is the wave vector associated to the plane wave, to the wave function. You know that you can deal with a non-periodic system, despite the fact that we have a periodic code. So if you have a molecule, you can deal with that by taking a large box with the molecule in the center. And if there is enough vacuum, the molecule is not interacting with itself, okay, within the next box. And so you are really simulating a molecule. If you want to simulate a surface in the same way, you can create a slab. So that means that you stop the periodicity in the z direction at some stage, and you put enough vacuum in such a way that this surface does not interact with the one in the neighboring cell, okay? And in the same way, if you want to simulate a defect, what you have to do is that you have to take a big box that is big enough such that this defect in the center of the cell is not interacting with the image in the neighboring cell. Okay, so you need to make convergence with respect to the amount of vacuum here and here, or the size of your system in such a way that the 2 defects do not interact with one another. Okay, so an important parameter that you have to deal with when you're using plane wave is the so-called energy cutoff. That basically defines your basis set. In the sum that we had here before, we cannot do the sum up to infinity. We have to truncate it. So how do we truncate it? We truncate it by defining a cutoff, that is the kinetic energy of the largest plane wave that we will consider. So the kinetic energy of a plane wave is given by this here, okay? And so if the kinetic energy is smaller than a certain energy, we consider the plane wave in the sum, and if we are beyond that cutoff, we assume that the coefficient in the sum are all 0, okay? So basically, that's the variable is called E-cut, and that's defining a sphere in which all the G vectors are taken into account, and outside the sphere, all the coefficients are put to 0. So if you do that, there is a small problem. The fact that the number of plane wave is varying in a discontinuous way. So if you see the grid, the 2D grid that I've written here, the number of, so and these are my G vectors, so the small circles that you see here, okay? When I reach the sphere here, I have 4 G vectors in the sphere, and it's gonna be remaining the same until I reach the next one. So basically you see this number is static 4 until I reach the second sphere here. When I reach the second sphere, I will have 8 more points, so I will be at 12, okay? And I'm gonna be staying at that number until I reach another one, another sphere, which includes 4 and so on and so forth. And so you see that the number of plane waves that are taken in the sphere of cutoff is changing discontinuously. And so if you do a calculation, and the same is true, actually, if I change the lattice parameter, when I change the lattice parameter, the reciprocal lattice is going to change. And so the number of vectors, if I reduce, for instance, the lattice parameter, my reciprocal lattice is going to expand. And so some of the points are going out of the sphere, okay? And again, that's going to be done in the discontinuous way. And so as a result, if you do a plot of the energy as a function of the lattice parameter, if you fix the cutoff like this, okay, you will get something which is wiggly like this one here, okay? And the same for the pressure, okay? So to go beyond that, there is another parameter that is used in Aminit that basically, rather than saying rather than going up to this cutoff and saying, okay, up to this cutoff, my coefficients are non-zero, and above the cutoff, they are 0. What you do is that you define some transition region. You define some transition region, which is such that when you are below this value, E-cut minus this new variable, you consider them not to be 0. Above E-cut, they are 0, and in between, you're going to do some smoothing of the coefficient to bring them slowly from a non-zero to a 0 value. And this is called E-cut SM. That is a variable that is used to smooth things like this. So basically, the plane wave, this is a natural and simple basis set because we have this a block wave function and we have a periodic system. And the details in real space, they are described. If their characteristic length, so if you have a wave function that is oscillating a lot, you need to pay attention to that because that's basically related to the inverse of the largest wave vector norm, okay? And so the quality of your plane wave basis set is easy to increase. You just increase the size of the sphere that you have there, so you just increase E-cut, and you can increase the quality of the basis set because you are taking more and more oscillating plane waves. And so you are able to describe more and more shortly oscillating features in the wave function. The problem that you have in doing that is that if you have a strong oscillation, you need a lot of plane wave to describe that, and that's very annoying, especially to describe the core orbitals or oscillation close to the core orbitals. And so pseudopotentials are used to get rid of that. And this pseudonization kind of eliminates the need for for quickly varying wave functions. So how is it done? It's basically, and I'm sorry again for my slide, I will change that. Basically, there is a first assumption that you make, which is that you assume that the electrons that are close to the core, they are not varying too much compared to the isolated atoms. And so you freeze the wave functions for those electrons to their wave function in the isolated atom. Okay? You're assuming that the wave function for the core electron is the same as for the isolated atom. And so you split the density into a part that is related to the core and a part that is related to the valence electron. And for the core, you assume that the wave function are those of the atoms. Okay? That's the first part. But so depending how you define what is the core and what is not the core depends on the system. And again, there's plenty of things that should have been in in other places. But okay, for the fluor atom, so the yellow is supposed to be on the 1s2 here, and the blue is supposed to be the valence band, and is these ones. So here the separation between the two is kind of clear because we have kevs here, whereas here we are 10 to 100 of eV. Okay, so there's a big difference between the 1s and the 2s and 2p. If you look at this one, the separation is less obvious between the 3s 3p and 4s 4d. So in the upper part, the blue should come up to here, these four, and in the lower part, it would be this one. And the reason for that is that if you look at the energies, it's something like 50 and 100 here. The separation is less pronounced than in the first case. Okay, and so you can either have a pseudo-potential that considers that these four should be valence electron, that is called small core, and this one is one in which these two only are the valence electrons. So depending on the material, there is a big effort that needs to be done, and there's a website that is called the Pseudo Dojo that you may have heard of, where we provide good quality pseudo-potentials that are based on comparison with all electron calculations. So the idea then is to separate the core electron and the valence electron in the functional, and so there's a formal way to do it. And then you can get an expression for the energy, and one way to do that is to consider an ionic potential, which is the potential due to the nuclei plus the part that is due to the core electron. And when you do that, you can write a formal expression that gives you the energy for the valence state only, okay? That requires only the wave functions for the valence. The external potential is now due to the nuclei plus the core electrons, okay? And then you have the R3 that is only for the valence electron. For the exchange correlation, you see that in principle, it should be the full density, so the one that includes the core electron as well. And as a result, you may have heard about something that is called the nonlinear core correction, because in principle, even if you use only the valence electron, sometimes the effect of the core is cannot be just adding the density of the core electrons. Okay? So the idea of the pseudization is to replace this Schrödinger equation, where the wave function is in principle oscillating still quite a lot close to the core, because even if we have frozen the core electron, the valence electrons need to be orthogonal to the core electron, and as a result, close to the core, there are strong oscillations, and so the cutoff that you would need in that case would still be big. And so you replace this Schrödinger equation by another pseudo Schrödinger equation in which you put a pseudo potential that is smoother than the other one, but you want that the eigenvalues are the same as before. So what you do is that you make this pseudo potential smooth for below a certain cutoff in radius, and so the pseudo potential above that radius is going to be equal to the ion potential. The wave function is the same, so below the cutoff, it's going to be smooth, and beyond the cutoff, it's exactly the same as the one that we had before. And you can impose some constraints, such as the fact that the derivative at the radius before and after the radius is the same. And as I said, the most important criteria is the eigenvalue should be the same. So there are different ways to do this. One is imposing the conservation of the norm, and so you may have heard of norm conserving pseudopotential. These are just pseudopotential in which, when you integrate up to the cutoff, the integral of the square modulus of the pseudo wave function is exactly the same as the one of the real wave. Okay, and then there are forms in which you can separate the pseudopotential into a local part and a non-local part that depends on R and R prime. And this non-local part is expressed on a basis of R spherical harmonics. Okay? And this is called the kernel. I'm sorry. Just move them because otherwise it's really messing you. Okay. So the no-local part can be written in two different ways. One, the kernel that I was showing in my previous slide, so this kernel here, okay, can be written in two ways. One is called the semi-local part, in which you replace the R prime dependence by a semi-local part times the delta, and a separable form in which you write that this potential is simply a product of two wave function, one of two potentials, each of which depends on one of the two variables. Okay? So the semi-local potentials are easy to visualize, these ones, but the separable form is much more efficient in terms of numerical treatment. And so there has been a development of a transformation from one to the other. And one just need to be careful to the fact that when you do this transformation, there can be fictitious eigenvalues that appear and that are called glucose states. And one need to pay attention to that. But again, there are websites that do that for you, as I was mentioning, that's the pseudo-dojo. So basically the idea is that you are replacing the wave function that, as I was mentioning, was oscillating close to the core radius by something which is smoother. So the all electron wave function is the green one, and the smoothed version is the blue one that you see here. It's much smoother and will require a lower cutoff. And the price to pay is that now your potential, which are pseudo potentials, they depend on the angular momentum. They are different from one angular momentum to another. So basically the Coulomb interaction that was produced in green here is replaced by a different channel for the potential for the different angular momentum. And with that, I think that I will stop here. I take questions.
In somewhere in slide, you are not using like R prime in space group utility. When you are using SPG group, then you are not using R prime.
So let me go back
For
to
example,
that, just to understand. So in an example that I was giving, or what?
no, just previous slide.
In my examples
Yeah, just back.
here,
No, just and go back.
back.
No, in somewhere in slides. I don't know.
Sorry, I'm sorry. Should I go back or should I
Go back, go back.
this one?
No, where you are using only SPG group, angle and ASL.
I mean, these are all my slides. I don't have more than that. So there's one which is about cubic zirconia. Okay, it's not this one.
No,
Okay, so this is the output. This is another way to write things. Is it this one?
no.
No. Okay, this is the last slide. There is no other slide than this one.
There is also R prime.
There is what?
No, in one slide there is no R prime value, or you are using SPG group.
No. I don't know which slide you're referring.
Yeah, this one.
Here.
Yeah, here.
You mean these two?
Yeah, this one, this one.
Hey, this is what I explained. So you can always use this. Okay? This is an alternative. Either you specify the 9 components of vectors, okay, or so that this is equivalent. So either you specify the 9 components of A1, A2, and A3, okay, or you specify the 3 lengths, A1, A2, and A3, the lengths, and the 3 angles. So when you specify this, okay, this here and this, these two are exactly equivalent. You choose whichever is more easy for you.
This below are in conventional unit cell or primitive?
You choose.
Oh.
In this case, it's a primitive unit cell.
Above this is primitive and below,
It's also primitive.
then how we decide in primitive there is some different R prime.
No, they are the same. This and this shouldn't be the output. They will be. So when you have 3 vectors, okay, you can define them by giving the Cartesian coordinates of the first one, the second one, and the third one. So that's 9 numbers. That's what I'm doing here. See, there's 1,
Yeah.
2, 3, 4, 5, 9 numbers. Okay.
Mm.
Okay. This is just a multiplication of the number.
Yeah.
Okay. So 9 numbers. There's another way to say it. It's what is the length of this one? What is the length of this one? What is the length of this one? What is the angles between them?
Okay,
Okay?
okay.
So with 6 number, you have enough.
Okay.
9 is too much in principle. And so what you do here is you give the 6 numbers,
Okay.
the 3 lengths and the 3 angles. This and this is exactly equivalent. Okay? You choose whichever you prefer. Yes.
I have a question. So, I'm curious about semi-code description, like the description of semi-code electrons. So,
So when you say the description is, you put them in the pseudopotential or you
Yes.
treat them as valence?
no, I put them in.
So you're not describing.
Okay, no, so the other one. Sorry. So, yeah, no, my question is, why, we still need pseudopotentials when there are codes which are all electrons?
Because it's way more demanding to do the electron calculation.
Okay, so that's it.
Yeah.
Yeah, because,
Yeah, first because you have more electrons to deal with,
yes,
and second to describe them, it's more complicated because just precisely they are the way function is oscillating. I mean, you know, if you look at the GW codes that are all electron, they are much more demanding.
also at the DFT level.
Also at the DFT level. And I mean, okay, then there's the thing that, as I was mentioning, the plane wave basis set is very natural for the periodic system. It's very easy to deal with. You just increase the cutoff and you're sure that at some stage you will converge. Okay, when you have an electron code, so to the best of my knowledge, there is no plane wave or electron code. So what they do is that they have a localized part that they complete. Right? So it's LAPW, for instance, but it can be tricky to deal with the core part. And when you want to increase the size of the basis set, it's not obvious. And in particular for the GW calculation, all the codes that are dealing with that are all electron, they sometimes have to put extra localized orbitals on the atoms to get something that converges faster in the GW.
And maybe most of them have numerical basis sets.
No, the only one that is numerical and that does GW to the best of my knowledge is FHI Ames. The other ones are not. So, for instance, exciting is LAPW. There's not that many all electron codes and the
In chemistry, since they use, okay, you refer to chemistry code, since they use the localized basis sets like Gaussian.
And in that case, when you have Gaussian, then it's very complicated to be sure that you converge. What is it that you add?
It's not systematical like waves Gaussian.
There are not many GW codes for. Yeah, but it's not many. I didn't say that there is, and I said there is not many. Yes, and there's a Mon GW, Turbo Mol now.
And they go
Which one? The ICF is not solely in both.
I think Amsterdam too.
It has GW as well?
Yeah.
The important point is also that when you push the convergence correctly, and if we can afford it, of course, the two codes, or let's say the two implementation, give the same results. We have even tested for the beta-salpeter, not just at DFT level, exciting and Abinit plus X or DP that you're gonna do this school, and you have to obtain with the two codes two superposed curves, and you can. Of course, you cannot do in plane waves just a 1s core of a very heavy atoms because you will need a billions electron volt cutoff. But if you can afford it, you can push it, and if you can increase the cutoff as much as to deal with semi-core states, you obtain exactly the same value. Because if you treat well the core in the full atomic potential, no pseudo potential, and if you put enough plane waves, the two are really on top of each other. Huh? This is something that we tested, it's perfect.
Here, that's also something in the same spirit, where 3 different GW codes are plane wave, all of them. So it's Yambo, Berkeley GW, and Abilit, where they're compared to one another. It's not the same approximation because there's a number of approximations, as you will see. But in that case, the agreement is kind of nice also. But also it was tested systematically in this paper. See that you need to do the convergence with the different code, and there's a good agreement.
Other questions?
I guess I have one. So with pseudopotentials, you mentioned obviously the non-conserving ones, but there are also these ultra soft pseudopotentials that are used a lot. Now I was just
Actually,
wondering,
people tend to use PW rather than.
yeah. But I was wondering, because obviously in certain codes like quantum espresso, which is what I use, you have to specify a density cutoff as well as an energy cutoff. I was just wondering when you use ultrasoft, for example, you need to use sort of a much higher density cutoff compared to your energy cutoff to, for example, a non-conserving one. So it's sort of, if I'm using a non-conserving pseudopotential, the density cutoff is like 4 times.
I mean, if you want to be exact.
Yeah.
Yeah.
So why is there like such a huge difference in the density cutoff that you need to have?
I mean, in principle, both should have exactly the same thing. I'm going to show you something. So do you see why they have to be different actually? I mean, why the cutoff for the density needs to be larger? Do you see that or not?
I think so, yes.
Sorry. It's here. So basically, you see when you have the density, okay, the density is the product of 2 wave functions. Okay, so you see that you have a J prime minus G that appears here. Okay, and so in principle, so if this is the sphere for the wave function, the exact sphere for the density needs to be the double.
Yeah.
This is true for any potential. Okay, so then what you do is that you make some assumption of the fact that, and that's often the case, that this part here is less important than. Okay. But in principle, if you want to be exact, you should take the factor of 4 that you're mentioning is the one that is exact. Okay. So if you're ready to lose a bit of accuracy in your density, you can reduce it.
Okay.
And from a mathematical point of view, that's 4.
I wanted to answer your question about the Van theorem for the case of degenerate. Okay. So for the case of degenerate ground state,
Because what I remember is that if P is a problem with the general C.
no. So you can check for example, the text Dreisler cross textbook about Dreisler functional theory. So the Van theorem has been demonstrated like Gian-Marco did, and then there is a section about the generated ground states. So what happens is that you have this picture. So you have let's say the set of possible external potentials. So for example, here you can take V1, V2, V3. Okay. So then you have, so this is the, let's say, the set of all possible external potential. Then you have the set of all possible, let's say, wave functions, ground state wave functions. So in the case of non-degenerate ground state, you have a 1-to-1 correspondence. So this is what C1. And then you have the densities, so this one. So this is the M1. So here you have this one-to-one correspondence, so it's a map in one direction. In the case of a degenerate ground state, you can have two situations. So you have two ground states. So this is not anymore a map. And then these two, and then you have two possibilities. So these two have the same density or have different densities. Okay, so let's take the case of different densities. So in this case, you have this one. And then you have the other case, for example, in which you have two ground states, different, but the same density. Okay? The Euler-Combe theorem is demonstrated not with respect to the single density or single ground state, but to the set of degenerate ground state, the set of degenerate densities, and then in this case, again, you have this set. So, in practice, what it is important is here in this case there is not anymore a map, while here there is a map between the three. In this case, there is not anymore a map, but what is important is that associated to a density, there is only one potential. This is the important point.
But was it demonstrated mathematically?
Sorry?
Was it demonstrated mathematically?
Yes. So they demonstrate, of course, the one-to-one correspondence between the set of the general density set. So this is more.
I mean, the part that we were discussing, we have not come to the density yet at that stage. We were from the wave function. So for the wave function, I don't see where you.
No, this is the lemma. So the previous lemma. So on the lemma there is not. Okay, this is only mathematical points are well described in some textbook, like for example, Dresden-Ross go going deep into mathematical issues, and also all these parts are let's say now formalized in a mathematically rigorous form by mathematicians, by applied mathematicians. So, for example, paper by Levy and Lieb have formalized Stolberg theorem on very rigorous process.
Yes, during the lecture for today, we didn't talk about spin, but we can include spin when you do a Abinit calculation. Yeah. Spin orbit coupling also. Yeah.
It is not in the basic tutorial, right? The spin orbit calculation.
Spin orbit.
It's not in the basic
it's not in the
tutorial.
basic tutorial.
But this is part of one of the tutorials? Okay, so in that case, if someone wants to try that tutorial, it will be on the website.
If you go on the there is spin at least. Yeah. So if you do the tutorial for the resource now. Good. Okay.
In the comparison you did for the G0W0, so they agree to what accuracy the different bolts?
Less than 0.1.
Less than 0.1, okay. It also holds for
If you take the same approximation, because as you would see, there is a number of approximations. That's it. So if you do the same things, they agree with it was less than 0.1.
It's for the bandgap or for the and for the ionization
I don't remember if we did that actually. Now I I'm not sure if we compare these. No. This is you see you have VBM, CBM, so
Yeah.
it's also again you see I mean the scale is the difference is less than 1. Here it's even way less.
Yeah, it's good. Good to know.